Salam and welcome everyone. So today we're going to be working on the question on the screen that says use Henry's law and the data in table 5.8.1 to calculate the solubility as a molality of CO2 in water at 25 degrees when its partial pressure is first of all zero point 0.1 atmosphere as well as 1.00 atmosphere. So we have to solve one question that has a partial pressure of 0.10, and when we're done with that we move on to the second question that has a partial pressure of 1.00 atmosphere. Now the first part of the question already gives us a direct instruction where we're told to solve this question using Henry's law. And Henry's law was definitely explained in chapter 5 of the Atkins Physical Chemistry 11th edition textbook. So, as for those of you who do not have the textbook, I am going to give you all that you need right now to solve this question because I do have the textbook. So, we're told to use Henry's law as well as data in table 5.8.1. Now, Henry's law, I've got three ways of describing Henry's law, and I'm going to explain all three for you. And the goal of explaining three of them is for you to be able to know the different ways the law can be applied, as well as to have different grammar in explaining it so that it's easy for everyone to like digest. So, Henry's law, okay, states that, okay, the first way of representing it is the vapor pressure of a solute is directly proportional to its mole fraction. So that's the first one. The second way of looking at Henry's law or of stating Henry's law is also Henry's law states that, okay, the second way, the partial pressure of a gas is of a gas above a liquid is directly proportional to its concentration in the liquid. So Henry's law also states that the partial pressure of a gas above a liquid is directly proportional to its concentration to the liquid. That's the second one. Then the third one is simply Henry's law states that the partial pressure of a gas above a liquid solution is directly proportional to the solubility of the gas. Of the gas. Directly proportional to the solubility of the gas. Now, you're going to be like, okay, she's written a bunch of stuff, and I just thought this was a simple, direct question. The truth is, a lot of physical chemistry questions can be very direct in calculation if you already know the formula, but direct calculation does not mean understanding of the concept and understanding actually what is going on as you're calculating. So that's why I'm here. So use Henry's law and the data in table 5.8.1 to calculate the solubility as a molality of CO2 in water at 25 degrees when its partial pressure is 0.10 atmosphere as well as 1.0 atmosphere. So the first Henry's law is telling us that the vapor pressure of a solute is directly proportional to its mole fraction. When you have a question that involves you to use Henry's law and you're dealing with vapor pressure as well as mole fraction, you're going to be using this particular formula. So it's just going to simply be P sub B, okay, is equal to X sub B multiplied by K sub B. So where P sub B is just simply the vapor pressure, okay, the vapor pressure of, let me just write it here, the vapor pressure of solute B, okay? By the way, you know how Raoult's law is for solvents? For Henry's law, you're dealing with solutes here. So it has to be a solute that is dissolving in a solvent, or solute that has lesser concentration in a solvent. So just basically what this is. So vapor pressure of solute B. So B is the component that is also a solute. Now, in this particular question, of course, our solute is going to be CO2, but I just want to use the B information to like fully explain what's going on here. So you have the vapor pressure of solute B, then you have X sub B is just simply the mole fraction, okay, of solute B. And then the third one, which is just simply the constant of proportionality, the Henry's law constant of proportionality. So Henry's law constant. And each constant would be each constant is unique to its gas, right? So for example, CO2 gas will have its own constant. That's the reason why we actually have a table 5.8.1. So anyways, this Henry's law, you use this Henry's law whenever you are actually dealing with vapor pressure and mole fraction. Now that I've explained the first one, now I want to move on to the second and the third. The second and the third have very similar formulas. We're told in the second one that the partial pressure of a gas above a liquid is directly proportional to its concentration in the liquid, or the partial pressure of a gas above a liquid solution is directly proportional to the solubility of a gas. Now, of the gas. Now, if you ever see partial pressure in a question, and you see concentration or you see partial pressure or solubility, you're not going to use this formula of Henry's law that I have explained when you have vapor pressure as well as mole fraction. You're going to use a totally different formula. And that formula is just simply P, okay? So this is the partial pressure of solute B is equal to molality, which is denoted as B. Or so you can see some formulas, they would say P sub B is equal to M sub B, where M is the molality, and then of course B is the solute. But some other textbook would have B sub B. So whether you want to use M for molality or B sub B is your choice. The reason why many people might avoid using M is because M is what you use to determine the mass. In questions like this, your molar mass. So when it already has mass and molar mass, you can just give it its own unique symbol, which is just B. So B sub B, which is just the molality of the solute B, okay, multiplied by K sub B, where K is the constant of proportionality of the Henry's law, or Henry's law constant of proportionality. So constant of proportionality for the Henry, so basically the Henry law values, okay, because each value is going to be different depending on the compound or the molecule in question. So CO2 values constant of proportionality is unique to CO2. So that's just basically what I'm trying to say. So in the research section of the Ask Physical Chemistry 11th edition textbook, you're going to see a bunch of constant of proportionality values for Henry that obey the Henry's law for different molecules and compounds. So again, what did I say? The B sub B, P sub B is just simply the partial pressure as well. And then the B sub B is just simply the molality of solute B. So yeah, so that's it. That's what's going on here. Now, if you go back to the question, now you can determine which Henry's law formula you're supposed to use. We're told use Henry's law and the data in 5.8.1 to calculate the solubility as a molality. Okay, it's kind of looking like the second formula I gave you of CO2 in water at 25 degrees when it's partial pressure. Okay, so we are going to be using the second one. So the partial pressure is just simply P sub CO2, because in this case, CO2 is the component that we're dealing with, or the solute that we're dealing with. So remember, they said CO2 in water. So that just means CO2 is the solute and water is the solvent. So P sub CO2 is equal to the molality. So B sub CO2, CO2 being the solvent, and then K sub CO2. So that's basically what you have. Now, the next thing you have to do is you already know that we're solving for B sub CO2. So B sub CO2 is really what we're asked to find. They've already given us the P sub CO2. So we're doing the first question. P sub CO2 is 0.10 atmosphere. Okay. And then we have the K sub CO2 value. What is that? What is that? Again, the question says we should go to 5A.1, the table 5A.1, And looking at the 5A.1 as well as the research section of the Atkins Physical Chemistry 11th edition textbook, we see that the constant of proportionality for CO2 when you're dealing with Henry's law is going to simply be 3.01 times 10 raised to the power of 3 kilopascal, okay, kilogram per mole. So that is basically what's going on here. Kilopascal, okay, kilogram per mole. So this is the value right here. And we also have this one. Right now, to solve for this question, B, okay, sub CO2 is the same thing as P sub CO2 divided by K sub CO2. So that is what's going on here. So now you're going to be wondering, okay, let's just substitute. Well, we can't just substitute. Why? Because the units for pressure don't match. We have atmosphere here, we have kilopascal here. So we have to convert from either kilopascal to become atmosphere kilogram per mole, or convert just atmosphere to kilopascal. So I'm just going to convert, okay, from atmosphere to kilopascal. And if we remember correctly, 1 atmosphere is equal to 101.325 kilopascal. Hence, 0.10 atmosphere is going to give us, is going to end up becoming just dividing by 10. So that's just going to become 10. Okay. So we're going to divide this one by 10. It's going to be 10.1325 kilopascal. So this is what we're going to substitute in our partial pressure value. So B, okay, sub CO2 is just simply going to be the P sub CO2, which is now 10.1325 kilopascal, divided by K, which is constant of proportionality, which is 3.01 times 10 raised to the power of 3 kilopascal, kilogram per mole. Yay. So you cancel out the kilopascal, cancel out the kilopascal. When you cancel them out, you can input 10.1325 divided by 3.013 times 10 raised to the power of 3. You can do the calculation. Or B sub CO2 is just simply going to be 3.3663, okay, times 10 raised to the power of negative 3 mole per kilogram. So that's basically what this is. When you do the calculation, this is what you get. Now, if you've been watching my videos, you know me already that I would never leave my answer this way, because I am a scientist, I'm a chemist, and I also know that it's very, very important whenever you have questions like this to make sure that you make your work as neat as possible, and you have to put in the proper number of significant figures. And the proper number of significant figures is going to be 2, because that is the lowest number of significant figures in all the values that we use to calculate this question. So we're going to solve this, and we're going to have our final answer to be in 2 sig figs. So B sub O2, so the molality of carbon dioxide, right, is going to equal, it's going to be approximately 3.7, okay, times 10 raised to the power of negative 3 mole per kg. So that's basically the answer to this question in 2 significant figures. Now, some of you may be wondering, why did we go from kilogram per mole to mole per kilogram? Do not forget that we've canceled all the units up top here. So really, we're just having 1 over all of these units. And an inverse of something is just the reciprocal or a flipped one. So for example, if I say 5 over 8 is raised to the power of negative 1, or 1 over 5 over 8 is the same thing as 8 over 5. Even though this is a seemingly simple thing, I do know that whenever you're overwhelmed, you may not be able to think through even like basic math skills, even if you're like studying engineering or chemistry or whatever. I just wanted to explain that. So it just flips because of the inverse. So yeah, that is how you solve this question. So we go on to the second one, which is just 1.00 atmosphere. Remember, the formula we're going to use is P sub CO2 is equal to B sub CO2 multiplied by K sub CO2. So yeah, that is what it is. P sub CO2 is equal to B sub CO2 multiplied by K sub CO2, where B sub CO2 is going to be the molality, okay? That is molality of CO2. We know the P sub CO2, which is what we're actually supposed to solve for. We don't know what that is. The P sub CO2, we know that to be 1.00 atmosphere. And we know the K sub CO2 because it's still the same solute. It's just 3.01 times 10 raised to the power of negative, sorry, times 10 raised to the power of 3. My mistake. Times 10 raised to the power of 3 kilopascal kilogram per mole. So, and of course, because we've got kilopascal here, we either have to change from kilopascal kilogram per mole to ATM kilogram per mole, or we change from atmosphere to kilopascal. And the easier thing to do is honestly to change to atmosphere, um, from atmosphere to kilopascal. So we convert from atmosphere to kilopascal. So 1 atmosphere, for all of you scientists, you're supposed to know what 1 atmosphere usually equals in all the pressure units. So 1 atmosphere is usually 101.325. It is 101.325 kilopascal. So 101.325 kilopascal. So make sure you also like review this with the other pressure units like um the TOR, so mmHg, what 1 atmosphere is with bar, with kilopascal, with pascal, and with a lot of other pressure units, because you have to try your best to have them in memory. If you've done chapter 1 to 5 of this textbook, you should have that knowledge by now. So, and if you don't, no issue, just go and review it. So you have 101.325 kilopascal. So definitely B sub CO2, which is P sub CO2 divided by K sub CO2, is simply 101.325 kilopascal divided by 3.01 times 10 raised to the power of 3 kilopascal kilogram per mole. So cancel out the kilopascal and kilopascal. So yeah, when you cancel that out, so B sub CO2 is equal to 101.325 divided by 3.0 times 10 to the power of 3 will simply just be 0.033663 mole per kilogram. So yeah, that is basically the answer. And of course, we're scientists. We're not going to leave our work in the raw values. We have to do in the proper number of sig figs. So if you look at this question, all that we use to solve this question, the lowest number of sig figs is in 3 sig figs. So 3 sig figs, 3 sig figs. So our answer is going to be in 3 sig figs. So B sub CO2, so the molality as a solubility of CO2 in this question for 1.00 atmosphere is just simply 33.7, okay, times 10 to the power of negative 3 mole per kilogram. And that's basically the answer to the question, meaning you have 33.7 times 10 raised to the power of negative 3 carbon dioxide per carbon dioxide moles per kilogram of water. That's just basically what this is saying. So again, 33.7 times 10 to the power of negative 3 number of moles of CO2 per 1 kilogram of water at 25 degrees. So that's basically it. Remember, even if you go back to a little bit of your science, you see that molality is just the total number of moles of solute per kilogram of solvent that is dissolved in. So yeah, that is comes to the end of this question. If you have any questions, please do not hesitate to write it in the comment section. I am here to help. If you're a student who is struggling in any of your STEM related courses, whether you're in middle school, high school, or university or college, make sure you email me at shahabitutoring@gmail.com. I help students succeed in all their STEM related courses, as well as I mentor them to be the best version of themselves in academia. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.